Well, hello, chemistry students. We are going to start our next unit, Unit 2, which is called Toxic Tides. It focuses a lot on water and all unique features of water. Today we're going to deal with the states of matter and some phase changes. This should be quite the review from middle school, but we're going to add a little bit of a twist revolving around energy and how energy affects the molecules of the various phases. So our objectives today is to be able to make conclusions about physical properties of water by describing phase changes at the microscopic level between solids, liquids, and gases as they relate to physical properties of water in the natural world. So let's start with states of matter and changing between states of matter. There are three major states of matter, and we know this from middle school. There's solids, liquids, and gases. You may have also heard of plasma. It seems like everybody, middle school kid, really likes the concept of plasma. It's like a super gas. It's an ionized gas. There's also on the low end, below the solids, something called a Bose-Einstein condensate, and that's where they take up less space. The molecules move very, very slow. The atoms move very, very slowly, and they can overlap with one another. It's called a Bose-Einstein condensate. We will not deal with either one of those. We're just going to talk about solids, liquids, and gases. Let's start at the top. Solids, they have a definite shape, and they have a definite volume, which means no matter what shape they're in, it's not going to change if we just let it sit on a counter. And they also have a definite volume. No matter what the size of the container is, it's going to still be the same volume. They have mass, they take up space, therefore they are matter. Matter is anything that takes up space and has a mass. In a solid, the particles are very closely together. They're vibrating, they are moving, but they're tightly packed so that we have this rigid structure, very organized. These guys have very little energy. The molecules are moving, but they're moving very slowly. You probably think of any solid as not being necessarily fluid. Your desk you're at right now, that countertop, the molecules and the atoms are moving inside there. But they tend to just vibrate in place. They don't move freely amongst one another. The next phase to talk about are liquids. Liquids are going to also have a definite volume, but they also take the shape of whatever container you put them in. So if I take a 2-liter bottle of soda and I pour it into a tray, it would still take up 2 liters. If I poured it into a large tube, it would still take up 2 liters. No matter what, that volume would be the same no matter what the shape of the container. But the big difference between liquids and solids is liquids will change their shape based on the container they're in. They have mass, they take up space, therefore they are a type of matter. These are the states of matter. In a liquid, the particles vibrate a lot more than they do in a solid, but they're still close together. They're just more loosely packed together. They're not as organized, they're not as rigid, so they will not necessarily be able to escape and move to wherever they want to. They just have to have the molecules moving freely amongst one another. These guys, on the relative scale, they have more energy than a solid, but not much more energy than a solid. And I've mentioned already, the particles themselves will flow around one another as opposed to moving just side by side like the solids did. The last phase of matter is gases. So gases, they are going to be able to spread out whatever space they're given. So for instance, if you take a balloon in this room, in the room you're in right now, and you release the gas from the balloon, that gas will try to occupy the entire room, spread out as much as it can. So they don't have a definite volume and they don't have a definite space or shape. That's what's different about gases. They take up the shape of whatever container is in its entirety, and they can be compressed or expanded because of their properties. They have mass, they take up space, therefore they are yet another state of matter. Matter is anything that takes up space and has mass. In a gas, the particles are rapidly moving very freely, amongst all the space in between them. They may collide with one another or not, as you see some of these collisions happening. They have a lot of energy. On the scales of energy, if solids are at the bottom, say a ranking of a 1, liquids are like a ranking of a 3, gases would be like a level 25. It's just that much more energy involved in a gas. If we were to break this down and summarize what I just said, if I look at solids, solids have a definite shape and a definite volume, and they have the lowest of the energies. Liquids have an indefinite shape, meaning they take the shape of the container, but they have a definite volume, and they have a little bit more energy. And finally, gases, they have an indefinite shape and an indefinite volume, and they have lots of energy, much, much greater than the solids and the liquids. So what happens as far as when they go from one state of matter to another? So solids can go to liquids, and liquids can go to gases, and gases can go to liquids, and liquids can go to solids, and solids can go to gases, and gases can go to solids. There's all these different combinations of how we go from one state to the other. Sorry about that. Okay, so talk about the different states of matter. There's that plasma up there, different types of states of matter. What would it take to go from one state to another? Here's what happens. You have to add or remove energy. The amount of energy that's in the molecules determines what state it's in. So if I have a solid and I add energy, like I heat it up, it's going to become a liquid. It's going to melt. And if I take that liquid and I add energy, it's going to become a gas. It's going to boil or evaporate. The energy, when they're added to the particles, they make them move faster. Okay, so if we say that solids have the slowest amount of energy, when we add energy to turn into a liquid, the molecules move faster as a liquid than they do to a solid. Vice versa, if I take energy away, say by putting it in a freezer or refrigerator, then as I take the energy away, the molecules are going to move slower. So if I have a solid and I add energy to it, I'm going to get a liquid. The energy is being added to the solid that's going to allow them to become liquids. If I have a liquid and I add energy, well there I'm going to turn it into a gas. Now the gas has the energy that is in excess of what was in the liquid, and they have the very, very much greater movement of the particles. So what about these phase changes, all the different possibilities? So I'm going to go through every single one of the phase changes and talk about what goes on a molecular level as well as a macroscopic level. So what is a phase change? It's when one state of matter changes to another. For instance, as a solid becomes a liquid that is melting, as a liquid becomes a solid that's freezing. They all have names. As a liquid becomes a gas, that's vaporization. There's two different ways to vaporize. And as a gas becomes a liquid, that's called condensation. The phases change their state of matter, but they do not change their chemical structure. Let me say that again. When you undergo a phase change, the molecule itself does not change, its arrangement changes, and that's it. So one of the things that we use here to try to explain better about what's going on with these phase changes is this concept called kinetic theory of matter, or KMT, kinetic molecular theory, KMT. It just says that matter is made up of particles, and we talked about a few seconds ago that the particles either move slowly or quickly. They're either touching one another or not. Kinetic energy is the energy of motion, which means if the molecules are moving, they have kinetic energy. If they're vibrating, they have kinetic energy. And the amount of kinetic energy is dependent on how fast the molecules are moving. The faster particles move, the further apart they move. Now, one thing to realize is temperature is, especially the Kelvin temperature, is directly proportional to the amount of kinetic energy a sample has. Simply put, if a molecule has a higher temperature, it's going to have more kinetic energy. And vice versa. If it has a lower temperature, then it's going to have less kinetic energy. So as long as the temperature is changing, you're changing the kinetic energy of the molecules. You're changing the energy of motion. So what happens during a phase change? Well, you either add heat or remove heat. The heat is either going to be absorbed to make the molecules move faster, or it's going to be released to make the molecules move slower. When the heat's absorbed, they move faster. When the heat is released it is going to move slower. So let's look at each of the phase changes. Melting. That's when you go from a solid to a liquid. Again, like I said, this is going to be a lot of review here, but we're going to use a different type of language here. So when you go from a solid to a liquid, that's melting. What's happening there is the solid molecules are moving faster to become the liquid molecules. It almost always happens by adding heat, and what happens is that attraction towards the molecules, as you add heat, the molecules move faster, so the attraction the molecules have for one another decreases. And once they decrease enough, then those solids, which are nicely packed, will be able to move freely as you overcome the amount of energy that is holding the molecules in an organized fashion. Every substance has a different melting point. So, for instance, ice is at 0 and butter's at 33, 34. Every substance is going to change from a solid to a liquid at a different temperature. When you're going through the melting phase, you have the molecules are closely packed together as a solid. You add the energy, they tend to vibrate more and more and more and more and more until they get to a point that they move so fast that their vibration overcomes that attraction that's holding them in that organized fashion. So as you add heat, the molecules move faster, they vibrate faster until they break that attraction, the attraction that holds the molecules together in a solid state. Once they break that attraction, they can move freely and become a liquid. There's another weird one, sublimation. It happens with all substances, but just not at atmospheric conditions. The one that we're most familiar with it happening is dry ice. Dry ice, which is just simply solid carbon dioxide. It will go from a solid ice directly to a gas. There's no liquid state. At room temperature and room pressure, atmospheric pressure, carbon dioxide exists as a solid if it's compressed, and it goes directly to a gas without becoming a liquid. That's why it's called dry ice. There's no liquid state there. That phase change is called sublimation. The reverse of melting is freezing. When it goes from liquid to a solid, they slow down. How do they slow down? You remove heat or energy from the system, so you lower the temperature. You lower the temperature enough that sooner or later the attraction between the molecules is sufficient to have the molecules come in contact and become more organized. And look at that, the same melting points are actually the freezing points also. So ice will go from a solid to a liquid at 0 degrees Celsius, but if you're removing heat, it will go from a liquid to a solid at the same temperature, 0 degrees Celsius, saying that the temperature of the freezing point is equal to the temperature of the melting point. So how do we differentiate? Well, if you happen to be above the melting point, freezing point, that temperature, then the substance is going to be in its liquid state. If you're going to be below the freezing melting point, that means it has too little energy to go into a liquid state, then you're going to be in a solid state. So you can cool things down past that temperature to make them a solid, or warm things up above that temperature to make a liquid. Let's talk about the other end, liquids and solids. Liquids and gases. So the phase change that goes from a liquid to a gas is called vaporization. Now, there's two different types of vaporization. There's evaporation and there's boiling. Evaporation is when it goes from a liquid to a gas, but it doesn't have to be above the boiling point. The molecules that are in the liquid state are constantly moving, and some of those molecules will naturally go into a gas state. This happens at the surface where there's a lot of space. The molecules speed up, they come out, and they go into the gas. This happens best when it's close to the boiling point. On the other side, boiling is when that phase change is happening below the surface. You're heating it enough that the molecules, even deep in the surface of the container, are getting enough energy to become gases. That's why when you boil water, you normally see the bubbles forming at the bottom where it's closest to the burner. The molecules speed up, they move further apart, and they absorb enough energy to surpass the attraction that holds them together as liquid, and they become a gas. For water, boiling point of water is 100 degrees Celsius. That is also the condensation point. Condensation, that's the opposite of boiling or vaporization. It's when the gas is becoming a liquid. You've all seen, and this is a picture here of a soda bottle or a water bottle that's very, very cold. If you take it outside on a humid day, you'll get this water forming on the outside. That's condensation. Condensation is when you have the gaseous vapors cooling down enough that it become a liquid, and that liquid is in contact with the water bottle where it was removing or absorbing the heat from the gas. The gas molecules move slower until they become a liquid, and normally that happens by cooling. There becomes a stronger attraction between the molecules as you cool it down enough. And the opposite of sublimation is deposition. This is a phase change that goes directly from a gas to a solid. They move so slowly, they slow them down, cool them down enough that they jump right over the liquid state. You get a really, really strong attraction of the atoms towards one another. So here's another visual. As you add energy, it goes from a solid to a liquid to a gas, and as you release energy, remove energy, it goes from a gas to a liquid to a solid. The term for solid water is ice. The term for vapor water is steam. So again, what determines the state? Energy. Okay, so this represents what's called a heating curve. Now notice, on the left-hand side, there's the temperature as graphed. And from left to right, we are adding energy. So if our substance starts off as a solid, ice, and we add energy, it will increase in temperature until it gets to that freezing point, which is also the melting point. When it gets to the melting point, it will stay at a constant temperature. It will stay at a constant temperature the entire time that is undergoing a melting. As long as there is a mixture of solid and liquid, or like ice in a water, it's going to stay at that 0 degrees Celsius. For example, during the summer, you might have a glass of iced tea that has ice in it, and it's refreshing and cold and cool as long as there's ice in there. As soon as the ice is gone, the heat from the surroundings will go, instead of towards changing the solid to a liquid, it goes towards changing the temperature of the liquid once there's no more ice to change. Once there's no more ice to change, which is right down here, that water will increase in temperature as you add heat to it until it gets to, in this case it's water, to 100 degrees Celsius. At 100 degrees Celsius, then you start seeing a mixture of the gas and liquid state of water. And as long as the system, the water is boiling, under the phase change between liquid and liquid and gas, then the temperature will remain constant until that last little bit of liquid is gone and you have just gas, and then you could technically if you're able to capture that gas, you could heat it up and make it change temperature, get hotter and hotter. Key point, during a phase change, the temperature of the mixture will not change. There's two plateaus. The melting plateau down here and the boiling plateau or vaporization plateau up here, during that phase change, the temperature of the mixture stays the same. So let's talk about each section. When I'm in the ice stage, we already talked about the molecules vibrating. As you add more heat, the molecules vibrate more and more. And since the temperature is increasing, the kinetic energy of the material is increasing. Then you reach the melting point. During the melting point, the temperature does not change. It's going from a solid to a liquid. And as long as it's a mixture of solid and liquid, the heat that you add is going to go towards changing the potential energy of the solid, turning it into a liquid. So during the plateau stages, since the temperature is not changing, you're still adding energy. If you're still adding energy, that energy is going towards the potential energy of the molecules, making them vibrate a little faster while not changing the temperature. It says here that everything on the periodic table, plus all substances, have their unique melting and freezing points. The next phase is when we're undergoing just liquid. Well, that's where you're heating it up. The water gains kinetic energy. How do I know that? Because the temperature is changing. If the temperature increases, the kinetic energy of the molecules is increasing. So that's that second X area between C and D, is when it's just water, just liquid, and it's undergoing an increase in temperature until it gets to the boiling point. When it gets to the boiling point, you start having the liquid becoming a gas. During that phase change, again, it's a plateau. It's saying that you have a non-changing temperature, so the kinetic energy will not change, but since you are putting energy into it, you're changing the potential energy. You're changing the phase from a liquid to a gas. So the energy you put in goes towards changing the vibrations of the molecules to turn the liquid molecule into gas molecules. And then finally, once you've gotten rid of all the liquid, you're going to undergo a gas change. During that phase change, it is going to increase in temperature. So while it's increasing in temperature, you're having an increase in kinetic energy. Let's summarize. When the temperature is increasing, A to B and C to D and E to F, the temperature is increasing, you're adding kinetic energy. You're increasing the kinetic energy. When it's not changing, from B to C, from D to E, where the temperature is not changing, the kinetic energy is not changing, but since you're adding energy still, the potential energy of the molecules is changing. And then we talk about the weird exceptions, sublimation of dry ice and deposition. These are really, really rare. Probably the only substance that's even remotely familiar to you that goes through sublimation is dry ice. So let's wrap this up and just ask a magic question. So, if water freezes, and the Chesapeake Bay is full of water, right? Why does the bay not freeze completely solid? Well, if you think about it, water is incredibly odd. Water is weird. There's one substance in the world where the solid state is less dense than the liquid state, and that's water. How do I know that? Ice floats. With all other substances, as the material goes from a liquid to a solid, the solid is going to be heavier and more dense than the liquid, and it's going to sink. So let's say we have, and let me see if I can make my marker work here. Let's say we have this lake. And the lake is full of water. That's terrible. As it gets cold, this top surface will turn into a solid. So you can like ice skate on a pond or ice skate on a lake. But what that does is it provides an insulation that allows this area below to never go below 32 degrees Fahrenheit or 0 degrees Celsius. That's great, because if water was like everything else, again, let's take this fictitious lake that I just drew and try to draw a water. Okay, there we go. If this were like everything else, what would happen is, as it solidified, as it changed phases, you would get this layering of the solid on the bottom of the liquid. And ultimately, you can see the top is not protected, is not insulated from the elements, and this entire lake bed would freeze, become solid, and everything that's in there would die as it's frozen. That doesn't happen in our Chesapeake Bay, because we get this insulated layer on top that keeps the elements from coming in contact with all the water. Yes, that top layer will get thicker and thicker the colder it is. When we had a little freezing spell back in January and in February, that layer got thicker and thicker on lakes, ponds, and even on Chesapeake Bay. But it's still, the water below stayed above 0 degrees Celsius, which means any living creatures that were in that water would not freeze and they would not die. So the main reason that Chesapeake Bay does not freeze over is because water is weird. Water freezes, undergoes a phase change from a liquid to a solid, and is the only substance that I know of where the solid is less dense than the liquid. It's good for us. Things can live in water throughout our really sometimes pretty frigid winters. This even happens like up in Alaska in the Arctic Circle. There's still water below the surface of all those ice caps. So that's all I have to share about phase changes in states of matter. Hopefully this was useful to you. I'll be back with another video on physical change, chemical change, quantitative and qualitative observations.